TTL Computer 2. Today, we're going to turn on our digital simulation for TTL Computer 2, and we'll be running through our first two programs. And let's just jump right into this. So I'm kind of in my running view here. So we can kind of see our hex display and our values and our instruction register and the data that's on the L bus, the write bus, and the data bus. And we can also see our control signal outputs, and we can see a little bit about what's going on with the ALU. And again, we can also see our address bus data, or the address that's being accessed here. All right, so we're ready to go here, and I'm going to start our simulation. So our simulation's going. So first thing that you can see is our clock signals are not right. So this doesn't start up in a valid state. So we need to do a reset first thing. Okay, so now we can see that our clock signals look to be right. All right, we're at our negative clock, which is like our starting state. And here we're at instruction step tick 0. We can see a little tick display here. Okay, and when we get to our hardware implementation, this reset button, we will have a reset button, but we'll have just a simple, RC circuit that will just keep this low for a short time. That will bring up the clock and the computer right in a starting state, and the computer will just run itself without having to hit the reset. Okay, so we're good to go here. We're on our first tick, and we're in the first phase of our fetch phase, and we can see here that right, the counter out high signal is raised, and the memory in high signal control is raised here. So that's outputting from the program counter through the ALU into the memory address register, the high byte. And we can see also here that our ALU controls 1 and 2 are high, and that is that's our OR function that's being executed there. And our address bus is 0, and it looks like we have 0 on our data bus. Oh, let me back up a step. We didn't look at the program that we're running. Okay, so this is just a really simple program that we're running. And this is just the format of our assembler programs. We have the include statement, which includes the custom ASM definition for our CPU, all the instructions. And this starts our first program, right? So we have our bank statement saying that we want this to be loaded into our ROM. And then just two really simple instructions. We're just going to load A immediate with the value 80 hex. And then our next statement is going to be jump. And this $ means the current program counter. So what this is going to do is just enter in a loop, and it's going to continually jump back to the jump statement. So it's just going to load A with 80 hex and then stop itself in a loop with the jump statement. So that's what we're running right now. And all right, so we're just at our first tick. Now, if you remember, we have the 4-phase clock, if you want to consider that right now. So we have to clock this 4 times to execute the full tick, right? That's 1, there's P clock, 2, U clock, T clock, and back to the N clock. Now we're at step 2 in our fetch cycle, and we can see now it's counter out low, and we have our memory in low signal is raised, and we still have ALU 1 and 2 signals raised for the OR function. And that's low clock again. All right, now we're at step 2. And now we're doing, so we've moved the program counter to the memory address register. Our memory address register has 0. And now we're going to read that RAM. And we can see that we have our RAM out signal is raised, and we have our instruction register in signal is raised, and we're going to execute that. And we can see the data. The RAM out has 5, which is the load A immediate opcode. Okay, so we'll clock this again. Okay, so now we've loaded the 5 into our instruction register, and we're also starting the read of the data, which is we can see the hex 80 is here. Okay, we can see that our A in signal is raised, and we will just clock that in. Okay, so that's been executed. Now we're at the next instruction. You can see our address, our program counter is advanced to location 1. All right, so we executed that load instruction. Let's go to program mode. So the controller and all the control signals are released. And so now we can raise the A out, and we can see that our A register, in fact, has been loaded with the hex 80. Okay, so let's go back to run. Now, I'm not going to single step this. Let's just clock this through, because this is going to be the jump instruction. And our opcode for the jump is 39. And we see there's our opcode 39. Our address program counter is at address 2. I'll clock this through, and that's reading the rest of the jump statement. Our program counter is at address 4. Keep clocking this through. There, we just executed the jump, right? Jump is opcode 39, and now our program counter is back to 2. So we're now in the jump loop. We're stuck in that loop where it's just going to stay forever. Okay, so that was our very first program. What we're going to look at now is a test harness that I put together. Okay, and what this test harness does is I use this to validate all of the instructions. So there's about 35 or 36 tests cases that I developed, and so we'll just kind of look at the pattern here for the test cases. So the program starts out with just a no op. First thing we need to do is load the stack pointer to set the stack pointer up so that we can do call statements. And then this is the pattern for our test case, right? I load C with the test number that we're going to execute. I call the display routine, which will send that to our output display. Let's just dump down there. Right, here's our display routine. We take C and we load it to address 2001, which is our hard-coded address, our memory mapped address for our hex display. So this just loads C to the display, and it's that easy to load to use the display and the memory mapped devices. And this is just keeping track of the test number. And here's our little error routine. If we do detect an error, we will jump here, and it just loads EE to the C register and loads the display with EE. So we just see that is our error indicator, and then we just go into a jump loop if we hit an error. Okay, so that's our test case, and here these test cases start very simple and they build in complexity, and until they execute. Validate the full instruction set. So here we're just really, testing the load immediate values. We're doing a subtraction, right? And here we're doing a number of conditional jumps to give us opportunities to check an error, right? We're subtracting 2 from 2. So if that's not 0, we want to be an error. If there's a borrow, we're not borrowing. 2 from 2 should not do a borrow. That would be an error. So we should be in a not borrow. If we are not, there was no borrow, jump to test 2. But if there was, we would indicate an error. So that's kind of the format of our test harness. Okay, so I've compiled or assembled that test harness and off screen, and we're ready to run this now. So we're going to run this a little bit differently than we did last time, and we are going to set up or start a real-time clock, and we'll clock that at 1000 hertz. Okay, so we'll go back to simulation. We're starting our simulation here. So we can see again, our clock signals don't start up in a valid state. So we need to hit the reset. But we see our oscillator is in fact oscillating. And I'm going to hit the reset and we should start running. And there we are. And we're running through our test harness now. And we can see that cycling through. And we can see all of we can peek in on our running computer, our instructions and what's going on the bus. So we in fact are running through all of the test cases, and I said there's about 36 of them, and this is hex. So that's up to 32, and that's it. And running through. So we have no errors. And that is really important to have that test harness. I used it a lot when I was building, completing the design work, and allows me to refactor things and change things around and just run the test harness to see that we, in fact, didn't break anything. Okay, so we can switch this into program mode. And so you can see our computer just freezes in its tracks. Our clock did, in fact, stop on the not clock signal where it should. And here we can just peek in on the register set, right? Our B, what's going on in B, C, X, our stack pointer, FE, whatever the RAM is pointing to, counter out high, program counter out low. Okay, so you can see how we can use those, and we can just resume here, and that's running again. Okay, so that's it for today. So we saw how you can single step through the program in it with a manual clock, and we can observe what's going on. And we looked at how we could, pause the running program. We can use the switches to inspect, the register values. We didn't inspect RAM, but we could do the same thing with putting a RAM address in. And then we looked at a couple of our programs. We looked at the test harness, and we executed our very important test harness to validate our computer is functioning as designed. Okay, so in our next video, we are going to introduce our next 2 devices, and those will be a keyboard and a monitor, and we'll see if we can't get a command prompt running in those devices in our next video. So until then, that's it. Thanks for watching.